Hey guys, welcome to another A-level physics P5 video, and this time we're gonna go a bit recent. We're going to do the May-June 2017 P5 paper. Well, when you do the recent ones, you get a bit of an idea of the sort of thing they're into asking, so you pick up on the patterns. Besides, this kind of question is my least favorite because it really confuses me. Let's get to it. So, a student is investigating the motion of a small cube on a turntable connected to an electric motor, as shown in figure 1.1. So, here's the turntable. We have the cube, and the turntable is rotating because it is connected to an electric motor. Hopefully you all know the electrical symbol of a motor. If you don't, take a look at the physics syllabus booklet. At the end, they've given a list of all the symbols you should know. You're going to pick up on a lot of stuff you may not be aware of, and which you might, if you know, you may find useful in A-level physics P5 paper when you're drawing the diagram. I guess there was one for generator and there was one for oscilloscope, and I honestly did not know what the symbol of an oscilloscope was before. So, helpful stuff. So the cube is placed a distance r from the center of the turntable, and it is suggested that the relationship between r, that is the distance, and the maximum frequency of the turntable for which the cube does not leave, that is, does not move relative to the turntable, is given by, right? So what I do is that I underline this, and so I can actually know what the equation is saying. So what they're saying is that F and R are inversely related. So if F increases, R is gonna decrease, because the rest of this is a constant and K is a constant. So F and R need to be in an inverse relationship for all this relationship to hold true. And remember, this is F max, okay? And why does, like, from theoretical point of view, why would at a certain frequency it leave? Because what is holding the cube to the turntable? That is friction, right? And until friction is equivalent or greater than the centripetal force, the cube is gonna sit there. But the moment the centripetal force gets bigger than the friction, then the cube is gonna move. And what is the centripetal force equivalent to? It's equivalent to m into omega squared into r, and omega is 2 pi f. So hope that makes sense from a theoretical point of view. Though I think this particular knowledge isn't necessary for this question. Or it may be. Let's find out. M is the mass of the cube and K is a constant, so you automatically know that in this experiment you need to keep the mass of the cube a constant for all repeats in order to get a fair comparison of R and F. You need to design a laboratory experiment to test the relationship between F and R. So that is your objective, and explain how your results could be used to determine a value for K. So you have two objectives. Figure out the relationship between F and R and use it to figure out a value to determine a value for K, which is a constant. And do not forget to draw a neat diagram. That is important. On page 3, showing the arrangement of your equipment, and everything needs to be detailed. If there is a circuit, the circuit diagram needs to be complete. There shouldn't be any breaks. All of the symbols need to be correct. All of the symbols need to be at the correct position. The rest of the diagram has to be reasonable. There shouldn't be anything that is hanging in thin air. Just think of it like you making a plan diagram for someone who is a complete newbie and about to do a dangerous experiment. You're gonna have to be very thorough with your diagram in case the poor guy lost his shit, did something really terrible that got him hurt. The procedure to be followed, the steps you're going to take, the measurements to be taken when you're going to do the procedure. You're going to get some measurements which you're going to have to measure, and what sort of variables are you going to need to control. How are you going to analyze the data, that is the measurements you obtained. How are you going to analyze them to obtain your objectives, and any safety precautions. So 15 marks, at least 15 distinct points, that is a rule of thumb. Number 1, you need to identify the independent and the dependent variable. In this scenario, the independent variable is going to be the value of r. Obvious, because that is the one thing you can change easily in order to observe a change in the other thing. F, so the frequency at which the cube leaves, right? That is the dependent variable, control variable. At the top of my head, I'm going to say it's the mass of the cube. There may be others, we'll get to it. The procedure to be followed. How are you going to change the frequency? Confusing. Well, we do have a motor, right? And what does a motor do? You know it from your series in electromagnetism. In a motor, we have a magnetic field, and we have this current that is going through said magnetic field, and because of that, we're going to observe this deflection. And this deflection is basically what is giving us mechanical work, isn't it? So if we change the value of the current, theoretically we can change the frequency at which it deflects, right? That makes sense, doesn't it? So we can alter the frequency at which the turntable is rotating by changing the value of the current that is flowing through the motor that is controlling the turntable. Sweet deal, right? And for that, what you're going to need is a variable power supply, obviously, and also a rheostat and an ammeter. An ammeter to see that the current, that the particular value of the current that you're dealing with in a particular experiment is constant, and a rheostat to make some adjustments if there is a bit of a variation, a bit of a deviation, right? You need a complete circuit with a motor, and I guess a circuit diagram for motor is something like this. I could be wrong. I'm not really great with my symbols. I'll check this at the end so I'm not misguiding you. So it's either this like this, or maybe it's a circle, either of these. So we need a motor, we need a variable power supply, or we could just do with a normal power supply and a rheostat and an ammeter and a switch, so that the circuit diagram part of it is complete. And is there anything else? Obviously the cube is sort of gonna move, so it's a bit of a dangerous experiment. We may use some sort of a safety screen, so you're gonna be seeing the turntable from across a screen, from through a screen, so the cube hits the screen and not your poor eye. That is actually kind of in the safety precaution part of it. Anything else? How are you going to position the cube at the same spot each time? Well, you can actually, which point are you going to do? Well, you can actually sort of like mark the center of the cube. And you can like place that over that spot, or you can simply do that because we want the distance to be the same. Or you can actually mark that distance. That distance are from the center to the surface, which is going to be a bit easier. Variable control is important. And you want the turntable to be clean each time. You don't want there to be any sort of dust over there that is going to contribute to friction. That is going to increase the friction, obviously, and that is what is contributing the force that is keeping the damn cube where it is. So you want the surface of the turntable and the surface of the cube to be completely clean and dry, so no dust and definitely moisture free. These things are going to affect your results. So you're going to do, you can like gradually change the value of the current for a particular distance and observe the cube. And then you're going to reach a particular value in which you see the cube move. Now the intelligent thing to do is to do this again with a value of the current that is a bit less than the one that you just used for which there was a movement, and more than the previous reading for which there wasn't any movement. Because that value of the frequency or that value of the current isn't necessarily the one that caused the movement. There may have been a smaller value which caused it as well. Right? Great. So you get that particular value of the current, but what on earth are you going to do with the current? What you want is the frequency. And for that for that particular value of the current, you can just observe the turntable with a stopwatch and like time how long it takes for 3 revolutions. And if it's a bit hard for you to do that, you like make a mark over here that is gonna sort of like act as a reference point, and then you can like measure how many times this particular mark goes over this vertical position. So you're going to get the value of the frequency, right? You know the value of the R, you have all the values that you need, and hopefully we're going to do well with this. Variable control, I believe I mentioned the whole mass thing, the whole dry surface thing, because that is likely going to contribute to the friction. Data analysis, if you draw a graph of F and 1 over R, with 1 over R on the x-axis and F on the y-axis, and you get a straight line through the origin, then your data is valid. Easy peasy. And if you want to get the value of K, you're just going to have to take the gradient of F over 1R, right? So what is the gradient of F divided by 1R gonna be? It's gonna be F into R, yay. And then you multiply it by the mass which you would have made using a standard accurate electronic balance. And then you're gonna multiply by 4 pi squared to get K. Nothing too difficult. Safety precautions, have a safety screen in between the turntable and your goddamn eyes. I'd say that is pretty important. So let's go over this again. And this time let's make sure we're getting all the points right. So, in this experiment, the independent variable is the value of R, and the dependent variable is the maximum frequency which the cube does not move relative to the turntable, right? Could be 1 mark or 2 mark. Let's go with 1 just in case. The mass of the cube needs to be the same in each separate experiment with a different value for 2 marks. The part of the cube in relation to which the distance or from the center of the turntable is measured should be standardized. For example, the distance between the surface of the cube and the center could be taken as a way to measure R. So I guess that wasn't a very explicit way of saying it. You can say that the method or the technique of measuring the distance R should be standardized. For example, R can be taken as a distance between the center of the turntable and the nearest surface of the cube, right? As in the distance between here and here. Well, if sometimes you're going to take it as a distance between, say, the center and sometimes the surface, your data is going to be pretty unreliable. So the method of taking measurements needs to be standardized, right? A meter ruler is unsuitable for this measurement, or it may not be unsuitable depending on the turntable we are using. So we can go with either a meter rule or a tape measure, because a vernier caliper and is likely to be very small for the measurement. So we'll go with a meter ruler to measure R and a standardized technique for measuring the value for, right? Right. So independent variable to be controlled, the way the measurement of R needs to be controlled, what instrument we can use to value R. And the rest of it won't make a lot of sense unless you have a good diagram. So before continuing, let me make this. So let's just use this. Assume that the connections are sort of coming from somewhere beneath the turntable, because for the life of me I don't know how to quite draw that. Yeah, don't kill me for the whole skewed lines and stuff. So I think it'd be a good idea to put the motor in parallel. Reasons. Or it may work in series as well, to be honest. So let's just put it in series. And in reality, you don't want to cross the lines like I am. You should be drawing it like this, but so it's something like this, right? Have the battery over here. Again, you shouldn't be doing it the way I am. You should be neater with it. Stuff needs to be pretty clear. The diagram needs to be clear, and if it's not clear, it should at least be accurate in that you know what's going on. You can have a rheostat over here. and an ammeter over here. And you can like position a screen over here or something, label it screen, and labeling is important. Label this as the motor, the battery, the ammeter, and the rheostat, and this as the screen. This will give you marks, easy marks. Use the rheostat to vary the value of the current through the motor, and this variation in the value of the current through the motor is going to vary the frequency of the turntable. For a stable current, you can get the value of the frequency by simply marking a point over here and using a stopwatch, noting the time taken for a set number of complete revolutions, and then figuring out the frequency from that. And you can keep on increasing the value of the current by adjusting the value of the rheostat until you reach a frequency at which the cube moves. And then you start taking readings before that frequency. Like if you took it at, say, 0.5 and 0.6, and at 0.6 hertz it moved, you can take reading like 0.55 to see if it moved over there, to get a value for the maximum frequency for which it did not move. Obviously this is going to be liable to a lot of error, and there's only so much we can do to minimize it. And you're going to get marks if you clearly identify how you're going to use a reference point, like over here, and measure the amount of time this particular point is at the top to get the value of the complete revolutions in a given time interval. It's going to give you marks. You can also use a camera with a timer to do this. Makes for accuracy. Controller variables, I believe I already mentioned. Analysis of the data. Plot f on the y-axis against 1/r on the x-axis. If you get a straight line through the region, your data is going to be valid. In the gradient is equivalent to f into r multiplied by the mass of the cube, which you would have measured using an electronic balance, and multiplied by 4 pi squared to get a value of k. And the safety precaution is going to be the screen, so the cube does not hit you. And this is the way you're going to have to write it. They segment the sequence. So let's just take a look at the marking scheme to see how well we did and any improvement we could have made. So let's look at it. R is the independent variable and F is independent. 1 mark, guaranteed. Keep M constant. Yep, we did say that, did we not? Method of collection, showing power supply connected to motor, two leads within turntable, and the circuits must be workable. There should be a power supply connected to a motor within the turntable. So this has to be a part of the turntable, obviously. What we're showing is actually outside of it, and then the circuitry that is outside of it. Circuit ought to be workable. Method to change the frequency of rotation of the turntable. Adjust the output of the variable power supply or adjust the variable resistor. 4 marks. Increase the frequency until the cube moves relative to the turntable. Method to determine the period of rotation. Stopwatch or light gate attached to a timer. Data logger or stroboscope. F against 1/r. Straight line through the origin. Gradient into 4 pi square m. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're doing well. We need 6 more marks. Use the safety screen 10. 10 rotations. 11. 12. Actually, I forgot about the whole repetition thing. That is easy mark. 13. You need a balance to measure the mass of the cube. Wait for turntable to rotate steadily before increasing the frequency. Gradual incremental increase in frequency. I guess implied that, but wasn't really stated that clearly. Use a spirit level to check that turntable is horizontal. Or clean the cube at the surface. 14. Use a rule to measure. Or 15. These are full marks. I'm not 100% sure on the circuitry, how they mark the circuitry, because as AS82 students, we aren't all that into or aware of how circuitry works, how to present it as accurate as possible. So you may lose marks on that because they don't really show in the examiner report or give any example of how the circuit should be, but I think at least it was workable. Not sure if that is how it is in an actual turntable, but the circuit was definitely workable. Method to determine the center of the turntable. That is easy mark again. Sadly, I missed out, but we still got the full mark if the circuitry was alright. Method, measure 2 or more diameters, and the maximum distance idea is the point where they're going to cross is going to be the center, obviously. Hopefully, this was helpful. And if you like this video, please like, subscribe, and leave your comments. Thank you.